For those who are in person, thank you for your patience while we connected the Zoom meetings, but we are all here. In terms of registering and getting credit, I'm going to be looking at the Zoom, and everyone in person, I should have you checked in. The lunches are arriving at 1:30. Those on Zoom, I wish I could teleport you lunches, but I cannot. So just a quick intro of our wonderful student, April, who is an alumni of the Space program and made this event happen, and Jonathan, who is here as an ambassador of the program. I'm a career education counselor. My name is Shelby. We're hosting this event for you, and we will be following up with any questions that you have and helping you connect with future opportunities. But since I've already kind of delayed us, let's go ahead and get started again.
No problem. Thank you, Shelby. Hi, everyone. Hello, Zoom attendees again. I'm glad you can hear us. So we just want to clarify, we are student volunteers of the Lucy mission and the Space program. My name is April Labakin. I'm a second year returning college student here at GCC, majoring in mechanical engineering with an emphasis in materials science. I'm a non-traditional student. I had returned back to school back in 2018 and just trying to find my way.
Excellent. My name is Jonathan Mickelson. I'm a Lucy Mission Ambassador, and I just recently finished off my degree in 2021 in Leadership Studies from Humboldt State University, and I currently work for NASA. So that's two separate things, but there you go. So yeah, presentation. Everybody's able to hear. Good. Let's go to sharing. What I need to do is switch apps. Okay, so as feedback over here, I don't know if it's maybe looping through. That's fine, if it doesn't bother anyone else. So looking at this presentation, the goal of it is to kind of
Zoom.
Can't tell if it's going through the test.
Try again.
Test. That's better. Yeah, got it. So yeah, so the Lucy mission, how many people are aware of what the Lucy mission is? Have you heard of Lucy at all? A little bit? Okay, a couple. So Lucy is a NASA mission. It's a Discovery class mission that was launched a year ago in October. And as an ambassador, what I'm doing is just making sure that people know about the mission and also talk about some of the opportunities that are afforded from the mission budgets, which actually is what funds both of the programs that we were part of. So Lucy is, and I'm getting used to the touchscreen. So there you go. So yeah, a little bit about me, I guess, briefly. Lucy Ambassador, I went in the Space programs as well. There's 2 academies, and later on we're going to talk about what those academies are. Former business owner, currently employed with NASA now as a program analyst, and I love everything space flight, engineering, all that stuff, although I'm not an engineer myself. So yeah, when we think about the solar system, the first thing we think about is the sun and the planets. Obviously, that makes a lot of sense. But in addition to that, obviously, you have the inner planets and you have the outer planets, and you also have the asteroid belts throughout. So in addition to that, you have an inner belt of asteroids here. And there's a lot. We know a lot of those because they're close to the Earth. It's easier to observe. We can observe them through radio telescopes and other things. But all of these asteroids, whether they're inner belt or the outer ones, they're all remnants of the early formation of the solar system. So in the early solar system, it was a gas cloud, and all of the heavier bits, any of the slightly bigger rocks started collecting more, and eventually it created the big gas giants, and obviously then the inner rocky planets that we live on. These are fossils because these ones didn't actually coalesce into something, but it actually gives us a picture of what the early solar system looked like 4.5 billion years or so ago. So what Lucy is, I wonder if we can get this to go away. I don't know how to make that go away.
Drag it down.
Yeah, it disappeared before, but. Yeah, oh, well, let's do that for now. So Lucy is a mission that's specifically designed to go to the asteroids that are further out, and because these ones have been pretty much untouched by anything going on from the sun, a lot of the deposition that would have come from the sun is less likely to have affected them. So one of the things, the reason why this spacecraft is called Lucy, do you guys remember hearing, if you did anthropology, the Lucy skeleton? That's a picture of it there. It was found in Ethiopia in the 70s. But it unlocked a whole understanding about the way human development was, our origins. And in so doing, it kind of set a precedent for that. And so this mission is also going to find those remnants that are going to tell us a lot about the solar system. So here's kind of a picture of the actual asteroids and everything. You can see there's a ton of them, but there's this unique set of asteroids. They're kind of like, they look like two lobes, and these are called the Trojan asteroids. And what happens is Jupiter, because it's such a massive object, it actually kind of shepherds these asteroids into these clumps. And in these points, I don't know if you're familiar with orbital dynamics at all. There's Lagrange points, or Lagrange points, I never know how to say it right, but there's these points where the gravity is kind of equal between the big players in a gravitational system, and that's what these places are. And so what happens is, because the gravity is kind of balanced between the sun and Jupiter in these locations, those asteroids kind of stayed there for like ever. From the very beginning, they kind of formed, and once they got in those spots, there's nothing to move them away, and they're really far and few between out there, so they don't have as much like collisional activity as the inner belt asteroids that we're familiar with. So the reason this is important is because these little planetesimals, these little asteroids, what they do is they tell us what the solar system was like in the early days. This is going to help us understand the gas giant formation. This will help us understand the formation of the rocky planets and kind of some of the things that were in that gas cloud in the early stages, and that helps us understand our origins in the universe as well. So Lucy's data is great because it's going to give us all of the, like, it's going to let us like see what types of like volatile organic compounds are on these asteroids, what their composition is, what type of ices that are formed on them, and all of this is going to tell us a lot about the solar system. So this mission is really unique in another ways because it actually is it's basically a road trip. We are going to be going to 9 different asteroids, and that's actually the most that any other mission will have ever done. Usually we go out to an asteroid. I don't know if you remember, we went out to Bennu, and we can do some really cool stuff. But in this case, Lucy is really kind of taking the pulse of what's going on out there. So in doing that, we're going to go to these 9 asteroids, and the way we get there is actually really unique. It's going to take us about 12 years. The mission is going to be about 12 years long. So you'll be hearing about it now that you know about the Lucy mission. You'll hear things occasionally. In a couple of years, there's going to be another Earth gravity assist. And those are really awesome events. And we'll talk a little bit about what those are. Let's go here. So this is the Lucy spacecraft. It's 50 feet across. That seems kind of big. But the actual size of the spacecraft is about the size of a convertible car. And if you look at it in light of kind of the size of a person, that's about how big it is. It's a pretty cool spacecraft, and because it's going so far out to Jupiter, as you'll know with like other spacecraft, there is not a lot of, most of the spacecraft that we send out into the outer planets, they all used like radioactive nuclear isotope generators and stuff for energy. But in this case, Lucy is actually using solar panels. So Lucy is a new way of trying to do solar power generation for a really distant spacecraft. So it's a beautiful spacecraft. This is Lucy in its proving grounds where they were stretching out the solar panels. very beautiful. This is them from the underside. And this is Lucy kind of all packed up, getting ready for launch on an Atlas V. And then we sent it out to Florida and got it ready for launch. This is the encapsulated this is the encapsulated spacecraft inside of the shells that'll open up. And so that you'll see mounted on top of a rocket. This is where personally, I got involved with the program, and so did April. We got to go, because we were in the space program, which we'll talk about those academies. Because we were in it, we basically were quote unquote a part of the Lucy staff programs. So we got to go out to the Cape and actually watch it launch, and also meet a bunch of the people physically in the program, because this was 2020 and 2021 for both of us. So it was the middle of the pandemic. We didn't get to ever, see and hug each other or do anything yet. So this was really special to be able to actually get on site. And then this is Lucy on the launch pad. We also, got to meet a couple of the people for the different parts of the programs. That's John Dankenich. So Lucy launched a year ago, and that's one of the things that's interesting, is that we just came up on the Earth gravity assist. And so you'll see here, let's see if this will play. I think one of these is supposed to play here. Well, that's it. So starting at launch, right, you got the asteroids and Jupiter's all outside. And then we launched. So this happened a year ago in a month, basically. And this is the launch. So we actually, because we were there, we were out about 5 miles away from the launch pad. It was a night launch. And 5, 4, what it's like. 3, 2, 1.
Yeah! Wow! Oh my God!
Flight 180 talent utilization has gone close control.
Oh my gosh, look at that.
Did anyone catch the Artemis launch? That would have been really cool to see. That's for sure. So let's see the launch.
5.
And
The radius. The viewing radius.
what was that?
The viewing radius.
Yeah, we were at 5 miles away. The closest you can get is about 3 miles, and that's if you're actually working the launch. So it's very worthwhile doing. And you can get those kinds of tickets and that kind of access if you go to Florida. I encourage you hit Kennedy Space Center, and you can actually get access to those things. So as you'll see here, let's see if this will go back. You can see this animation. So when we launched, we actually launched Lucy off into like a little bit slightly different orbit than us. And so that's why we're here. And Lucy has now come back a year later, is because we lofted her on kind of a weak rocket when it comes down to it. It's enough to get her going, get her orbital, get her, she's orbiting the sun separate from us. But when she went out, she's coming back. And because of the way orbital dynamics work, you actually, if you throw a ball on one side of the planet, if you're floating, if you throw a ball like one direction or the other, you're going to see it go away from you. But what's going to happen is actually, if you go a full rotation, that ball will come right back to your hands, minus like miscellaneous friction and loss. It's really weird. So you have to apply a little bit more kick to get things to really start to move. And so that's what we are talking about happened last month, is called the Earth's first gravity assist. So Lucy came back by the Earth. This was like a month ago. And because of it coming right back, like the ball coming back to your hand, you can see Lucy's trajectory. Get that done. Look at that, that's beautiful. Lucy's trajectory came right back. It's like, it's insane. But it also means that Lucy had to thread all of our satellites. And this is just a simplified picture. You've probably seen how busy it is in low Earth orbit. This is all the geostationary satellites that we have out there. And one of the crazy things is that Lucy actually came back lower in orbit than the International Space Station by about 10 kilometers. So it came really close to the atmosphere. And by doing that, it actually stole a little bit of potential energy from the Earth, and it gave it a kick. It made it go 4.5 miles a second faster, which is a big deal when we don't have a lot of delta V in the rocket that sent us up. So what you'll see here is as we go, oh yeah, and then as it flew by, it took this picture, which isn't the best picture we have of Earth, but it's the first Lucy picture of Earth as it came back after a year in space. And you'll see that it's interesting. The closest it's ever going to be, even though it's going out to those Trojan asteroids, the closest it's ever going to be to Jupiter was actually at this point. Next time it's going to be going in places and it won't even be close to Jupiter, even though it goes as far out as Jupiter is. During that first Earth gravity assist, Lucy was able to come back. So you can see Lucy, this is Lucy right here streaking through the sky in Lancaster. Someone that was, you met them at JPL, right? Yeah, and they're astrophotography. So that's very cool. But as you can see, this is what happened with Lucy's orbit. She got kicked out. And you can see it's not enough to get all the way out to where she is, but that means she's going to come back by for a second Earth gravity assist. That's going to happen in a couple of years' time. And when that happens, she's going to get another kick and it's going to take her out. You'll notice that there's this little dot here. This is a small main belt asteroid. This is a small one that we know about here, and it operates as a good test bed for us to test out Lucy's systems before it gets to all of the big ones. So this is in the main belt, and then these are where the Trojans are that we're going to be going and hitting. So we'll do that. That'll happen in 2025, and then after that, she's going to continue on. This is that second Earth gravity assist. She's going to continue on out until she hits that first, and in this case, here's Jupiter. So you can see this is that leading lobe of the Trojan asteroids. And she's going to go to Euripides. And this one is it's just a cool asteroid. We know it's out there. It's old. It's big. So it hasn't really been touched and messed up. So it's going to give us a really good picture of what those asteroids are. And we just found out, because we've been studying those asteroids as a mission, because they're the targets that we're going to be hitting. We had some time with the Hubble, and Hubble Space Telescope was watching it and actually found that it actually has a small little satellite running around it. It's a little rock. We don't exactly know how big it is right now, but it's called Kata, and we're gonna see it. So now we've adjusted plans so that we can actually observe both of them and get something. The crazy thing is that the spacecraft is actually going to fly by these asteroids within about an hour's time. And in that time period, it's jetting by. It's going to be a speck, and then it's going to be like right there, and then it's going to be gone. So everything that happens with the Lucy spacecraft is kind of like a pointing nightmare in trying to find a needle in the haystack. So it's the second Trojan. You can see it kind of loops around within them. Here is Polymele. And this is also another very interesting asteroid. What we want to do is we want to take kind of the pulse of all of them out there, and we want to see, what do we know about them? Each time the spacecraft goes by one of these, it takes about a gigabyte and a half, a gigabyte and 1.25 gigs of data, and then it has to try to downlink all of that stuff to the Earth so we can see it. In this case, it's tricky because it actually went to Euripides, and then in not even barely a month later, it went to Polymele. So that's going to be tricky. We're going to have to download all that data. We might not even get all of it. We might have to store some of it and then get more of it later. So stuff starts really happening in the late 2020s. And we just found that in studying Polymele, we found it also has a satellite. So this is telling us something even now, before we've gotten through, is that it's quite possible that having binary satellites, for these kinds of asteroids is very frequent. And then after this, it's going to hit Lucas. And this one's strangely shaped, so we want to study it to kind of see why is it not, it's still just about as big as the other ones, but why is it called kind of shaped not as round as the other ones are? And then there's Orus. Oris is interesting because it's redder. We can tell, like, spectrographically, it's redder than the other ones. And we know that, like, I don't know if, did you guys remember seeing pictures from New Horizons when it flew by Pluto and Charon, the planets out there? Well, planetesimals, I guess. So there's in the outer solar system, a lot of them have this kind of reddish tint to it, which is like an organic compounds. And so we've been studying them there. We want to study them here because it's something that's a part of how they go. Then what's going to happen is Lucy's going to fly in. She goes real slow out here, and then she swoops back in by the Earth and is going to start a looping kind of course. So she'll come back in, we'll do a final course corrections. And then what's going to happen is she's going to come back out. Now you'll notice the positioning here. From Lucy's perspective, she didn't really go very much. She went in back where we were and then comes right back out to the same quote unquote kind of location. But what's happened is the whole outer solar system of planets has all been rotating this whole time. So now she's coming into the later lobe, the trailing lobe of asteroids behind Jupiter this time. So this is another set, and we're going to be hitting these two, which is really cool. Patroclus and Menoetius, sorry. And these ones are a binary pair. They're about the same size. They're shaped about like that. And they spin around each other with a barometric center. And they're actually really close. If you were standing on one of them and looked up at the other one would be like 5 times the moon in the sky. It would be really, really big. So they're close together. So we're going to fly past them. Yeah, got it. And in order to do all this, we're going to be using a lot of the equipment. Like, so we have our instruments, instrumentation, and these. Thank you. Excellent. So we have a couple of different instruments, the Lori, T2Cam, the Ralph, the Test. There's this thing that the Lucy mission did, is they started adopting everything because these like Lori is actually a type of camera that is black and white, and it's high resolution, and it was used by other spacecraft. So a lot of these are previously used. They're like copies of instrumentation that we used on New Horizons and other spacecraft. But for the Lucy versions of them, everything has a lull in the front of it mostly. So La Lori, La Ralph, La Tess. And you'll notice that the Space program also adopts that same kind of a thing. So Lori's big. What she does is she gets the New Horizons spacecraft. It's high resolution imagery in very small points, so we can get a lot of detail out of it. It's a great one. It shows us geologic features. La Ralph actually on the New Horizons flew after we went past Pluto and Charon. La Ralph took this picture, and it shows that same kind of reddish material, organic compound. So that's useful, and we're going to study that and find that out. La Ralph also is able, it's an infrared spectrometer, so that means it can detect the types of molecules that it's detecting. So it's really good at figuring out what kind of ices. Is it an ammonia ice? Is it a water ice? Carbon dioxide ices? In this case, it actually can see the difference. It can see this ammonia ice from a new crater that happened when it flew by Charon. Okay, and then we also have an infrared spectrometer. So OTES is this, and OSIRIS-REx actually used the same instrument when it went to Bennu. So it's going to give us some good pictures of the heat distribution, and that tells us about the materials and the makeup. Obviously, it's a spacecraft, and we send these things out. We don't send astronauts to to the far-flung edges of space yet. But we have a lot of people who make this happen, and this is it's just part of the team. One key aspect, you have scientists, engineers, project managers. In the aerospace field, you'll find that there's tons of people. It takes thousands of people to put something like this together, but there's also student interns, and that's part of the program we came into, was where you're learning about how to become a student intern, how you can get access to those. So it's really great to be able to do it. We'll talk about that in there. But part of the Lucy package, it's a Discovery class mission, which is like a $500 million mission, and it's a NASA spacecraft. But they actually earmarked a ton of the money in that where they didn't need it, they're like, hey, we know we could fit this. They put it into student outreach. And so that's why we're here, is our programs are all funded out of the Lucy mission budget. The Space program is the one for college students, where it's a student pipeline accelerator and teaches us a lot of stuff. The great thing about this all when you're thinking about Lucy is that Lucy itself, now that we've put it into this kind of resonance with the rest of the solar system, it will stay doing this for thousands or millions of years. It's going to swing in, it picks up a little speed, gets back whatever it lost, comes back out, and it just alternates going back and forth between each of the lobes. You can see it's hitting each of the lobes. So this actually gives us an opportunity for extending the mission. So if for some reason after this 12 years passes, Lucy's still happy, she's still taking pictures and doing everything that she needs, then we actually can extend that mission potentially and go visit a whole bunch of other asteroids out there by tweaking things here and there. So very exciting. Hopefully that helps you understand the Lucy mission a little bit. And let's see where we're going to go here. Part of the reason you may have heard this Lucy plaque. There's a plaque that we have, and you can see it. You'll see it on the website too, where it has quotes from different people. From some, I think George Harrison had a quote on there. Because this plaque's going to be, and the spacecraft's just going to be flying around, it's kind of like Voyager, where we'll actually be able to see, our ancestors or whoever, if they ever catch up to her, they could actually see what's going on with her. So 12 years, 9 asteroids. We keep finding more asteroids so that she's going to be viewing. So that might even go up to 10 or 11, who knows? And she'll be on this journey. If you want to find out more, obviously you can take the QR code of that and follow on here. Any big questions before we switch into the other part of the presentation? I didn't go to super detail. There's a lot of detail you could go into the instrumentation. So if any of you on the engineering side are into like remote sensing, my background is in geospatial information systems. So I love hearing about, all of the different kind of wavelengths that we capture and what they can do and stuff. So we could talk about that if you want to connect afterwards. Yeah.
So how come they went with like solar panels instead of like radioactive?
Yeah, it's a good question. So the radioactive isotope thermal generators, they are really expensive. And because we have, we don't do as much nuclear testing and nuclear, the types of nuclear reactors that we have now do not generate as much of those isotopes that we need for those. So it's actually harder to get, and we have to earmark them very carefully to specific kinds of missions where there's no other option. So in this case, the advancements in solar panel technology has happened like in the last 20 years. It's been a lot. And so there was an opportunity to let's try some really big panels and see if we can get her on a good, budget, a good diet budget of energy, then solar panels can actually do the job. So in this case, I think it's going to work really, really well. You may have heard when they launched and we pulled the solar panels in, one of them didn't close all the way. And there was some worry that was going to really impact things, but they got it down to I think it's 97% closed, and it's pretty much holding. So they're going to leave it there. It's good enough. She's going to have enough power, and and hopefully that'll actually help us. We'll get engineering know-how out of this, so we can do better systems and not have those solar panels get gummed up again for future missions. And also maybe we can do even more where we don't have to go back to radioisotope generators. You have questions? Yeah.
To be a student intern, do you need anything prerequisites or what?
No. So one thing that's really fun about us talking, so she's an engineering background, I'm not. I have engineering, I love engineering. But so yeah, we'll get into some of the prerequisites on the programs, but yeah, you do not actually need to. Yeah.
I'm actually curious about the camera. Why wouldn't you go with the cameras you chose instead of, I don't know, something off your iPhone?
Yeah, so because they're gonna be in space for long periods of time, they have to be kind of hardened for those environments. And also that the first one, the LORI that we were talking about, it's kind of like the most extreme telephoto lens that you can imagine. So, it's like a little chip, like way off there, but it's like super high resolution in that area. So it has to be really purpose built for them. Most of these instruments are actually built at college campuses. So they kind of come up with a design and then it gets built, and it got like LaLaurie got built for one spacecraft, and then we had that design and it worked really well. So they basically just made another one of them and then handed it over. So there's a lot of teaming up with universities and university engineering departments to create the instrumentation that goes on these kinds of spacecraft. And especially when you get down to some of the other spacecraft that are the shoebox size, the smaller ones, what's the term that's escaping me? CubeSat. So there's a lot of opportunity to actually get into imaging. And on CubeSats, we can actually use like a GoPro and tie that right in, and then you just can buy it off the shelf and tweak it a little bit so that you got a constant power supply. So a lot of fun engineering you can do there. Any other questions about Lucy? Okay. Let's switch over to
All right. Can you see it on Zoom? Okay, perfect. All right. So let me just switch
you could close that. Yeah.
this one.
If you don't have notes, you'll probably be just fine with what's on there.
I'm just going to. So again, my name is April, so I will be talking about I'll be sharing information about the LSpace program. So LSpace stands for Lucy Student Pathway Accelerator and Competency Enabler. So just it's so connected with the Lucy Space mission. Sorry, excuse me one second. Okay. So the creators of the LSpace program, these are the directors. Sherry Boonstra is the principal investigator of the NASA LSpace program at Arizona State University. She is also, it's also for the NASA Science and Mission Director. It's what helps funds the LSpace program, and which makes it free to students, undergraduate students like us. Dan Garcia is the deputy director of the LSpace program. So we, okay, so we have this nickname that we all call ourselves as far as participants, because it's LSpace. So he mentioned there's always L with something. So when as a student participant, you are already seen as family, so as La Fam. So this would be your La Dad and La Mom. And then there was a picture earlier of John Dankinich. He is the chief technologist at Marshall Space Flight Center. So he is also the instructor for one of the other academies, which I will explain. So we call him L'Uncle. So information about us. So the first academy is the Mission Concept Academy. Oh, I am going. So with this program, what you will be learning is how to develop a mission concept as a team. This is a virtual learning environment. You will be placed into student teams with your fellow peers. Preferably, well, LSpace tries to aim to place you within at least the same time zone as much as possible. And so you could be from different community colleges and universities, so it doesn't all have to be a specific type. And again, this is free. You will be learning from NASA scientists and engineers. You will be communicating via Zoom. And then currently, right now, the communication platform, as far as with typing, if you have any questions to reach out to the staff, would be on Discord as well. And so you'll be collaborating with your student peers to design this mission concept. And so what you'll be doing is, it's called a preliminary design review. It's a project that is a document that details the requirements, the constraints, costs, plans, schedule. Those are just the minimum topics that you would be adding into your project. So you'll be given an objective. So I will share with, oh, actually, before I do, applications are open now. The deadline is on Sunday, January 8th. It is, the upcoming spring session is going to be from January 17th to April 18th. Every Tuesday, you'll be meeting as a class from 4:30 to 6 p.m. Pacific time, and this goes for 12 weeks. So the session itself is 1.5 hours online, but when you meet with your team, that is a separate time outside of this. So we wanted to share, Jonathan and I, we were in the same Mission Concept Academy team, so we wanted to share a little bit of snippets as to what we did for our preliminary design review, or PDR for short. This is our team makeup, so you can see the different, the students from different universities and colleges. And so, you know, I did mention earlier, I'm mechanical engineering. At the time that I was attending Mission Concept Academy, I was a chemistry major. And so I was always interested in engineering. I got to meet more female engineer undergraduate students and peers, and so they helped encourage me to really just go for it. I still love chemistry, so I'd still go for material science now. So this ranges from freshmen all the way to seniors. So in the Mission Concept project, your PDR, you will be developing, you'll be in, your team will be in 4 subgroups. So you have your leadership team, you have your engineering team, your science team, and business. So Jonathan and I were the project managers of our team. However, the leadership team does not just do leadership. We also have to contribute into each of the additional sub-teams. So I cannot stress enough how important business is. I know as STEM majors, we love our science and or engineering, but business is a skill that you really want to learn to be a competitive applicant, both as a student and your future career. So your team, this is just, you know, simple. I mean, this seems a little bit complicated. Your team may have less than this and may have more than this. Really depends on what your concept is. So with our concept, we were assigned every semester, the parents, they will be assigning you a project, I'm sorry, a planet to focus on. When we participated fall of last year, our focus was on Mars. And so our objective was to find 100 metric tons of water ice. And then so we were given constraints as far as volumetric and size to be able to describe how we're going to plan this mission based on concept all the way up to launch and landing, and then how it's going to operate when it's at the landing site. This is our CAD rover. We selected a Pathfinder rover. We named her Poliahu, which is after the Hawaiian goddess of snow. She's so mechanically beautiful. And so the reason why we named her that, because we're looking for water ice and we're looking for a lot of it. The reason for this objective is, you know, we have the Artemis mission going on right now. So with the future Artemis astronauts that are going to Mars, we need water, excuse me, we need water as a sustainable life and for life support and infrastructure. So one of the other subtopics that you'll be adding to your preliminary design review is your mission schedule. What you're looking at in this slide right now is called a Gantt chart. It's a project management tool, which pretty much states what your tasks are as a team, the milestones that you're going to hit it at a specific time margin, because, you know, sometimes plans don't always go according to what you hope. And then all the way from defining the concept to manufacturing, this is all conceptual based. You are developing this. And so manufacturing, testing, verification, validation, including outreach, because you also want to educate the public. How are you going to have the public be aware of what your team is doing and why is it important? And so as far as the landing site selection, each team will be selecting a specific site. Every team has kind of their own selection and their own, they kind of get to choose. There's a little bit of creativity here as long as it balances with the constraints. So with the landing site selection, this is a trade study matrix. This is actually developed by one of the NASA scientists who was studying the different sites, landing sites, possible geographical regions of Mars. So the green area that you see here are the abundance of resources. The red just means that it's a limited amount of resources. Excuse me. So part of your PDR, you will be including your choice as to what type of technology you're going to develop. So is it going to be a lander? Is it going to be a pathfinder? Is it going to be, excuse me, an aerial transport like the Ingenuity? And so your team will be developing and using a CAD program. One of the best things you can do in LaSpace is to learn an additional CAD program. So as engineer majors, you are already learning other CAD programs like SolidWorks and AutoCAD. So when you're a student participant of LaSpace, you get free training sponsored by Siemens NX to learn their CAD program for free. And you get to also take the certification exam, which is very valuable when it comes to trying to get your applying for internships and for applying for a job. And the reason why the certification is very valuable is, when you pass and you get that certification, it tells your future employer that you are you're well skilled and you understand what the features are and how to do it, quickly. So you also want to tie in the science and explain how the different instruments are going to apply and how it's going to achieve your objective. And you also want to think about the risk analysis. You always want to think about what could go wrong, as little to the worst possible scenario, and how to mitigate it. So this is just a brief example as to, there are more parts to this in the preliminary design review. Our group's project PDR was clocked in at about 180 pages. So but you have a team of an average of about 10 peers. So you're not by yourself here, and it doesn't have to be over 100 pages. There are some who actually have, as little as 40 pages, but they're very concise. So the next academy that we're going to be talking about is the NASA Proposal Writing Evaluation and Experience. So this is taught by John Dankinich as well as the LaParents. And so it's also a team-based virtual environment. You will be developing a 7-page maximum. You cannot go more than 7 pages of a concept proposal of an innovative technology idea. So with the Mission Concept Academy, this is more of a mission idea versus, versus with MPW, which is for short for the NASA Proposal Academy, is more of your innovative technology. You'll be gaining experience not just with how to write a proposal, you will also get to learn the other side of it. You will learn how to evaluate proposals. And I believe this is probably one of the best academies, because sometimes you got to learn the other side of it to sometimes know, oh, maybe I could have added this or whatever it is. So while this is an academy, this is also a competition at the same time. And so your team has a chance to win $10,000 prize seed funding to advance your proposal, your concept proposal into manufacturing and testing, et cetera, and move forward from there. Application deadline, applications also open, deadlines on January 8th, Sunday. The spring session for FPV is January 19th to April 13th. This is actually every Thursday, 4:30 to 6 p.m. Pacific time. It's also 12 weeks long. And so keep in mind, you can only apply for one academy at a time. You cannot do both. That is too crazy. It's a lot to handle. So, although we cannot show you an example of what a proposal is, because this is where your creativity shines, as long as it balances with the metrics and shows that this is something very innovative and can improve the current state of the art. What you're seeing right now is an example of what's called a quad chart. A quad chart is the skeletal summary of what your proposal, is. So top left talks about what your goal is, what are the objectives that your idea is trying to achieve. Bottom left is your team overview. This shows this is just an example. So this shows 3 people, but with MPV, it'll be an average of about 10 students. And so top right would be the image of what that idea is. And this would be, it's not the final, it's just more of the first iteration or draft. And then the bottom right is, this is one of your most important parts of your proposal. It is the key performance parameters or metrics. What is the current state of the art of the technology that you're interested in, and how can it be improved based off of your idea? And so after your team submits the proposal, you'll be you won't really be within the same team. This is more an individual, but you will be working with your class peers, not just your team. And so these are just quick information as to what you will be training when it comes to evaluating proposals. And there will be a NASA reviewer that will help you understand what to look for, how to score it. This is an example of the rubric. So for instance, this right side here would be the numerical score, and what are the bases that falls within these scores? Why is it a 4.5 or to 5 or anything like that? And you would have to also write an explanation as to why. So in addition to the 2 academies, as long as you complete at least one of them, you will be eligible to participate in one or both of these additional programs that ListSpace offers, which is the Lucy Mission internships, and which is a 10-week internship. It's every summer. And then so the Lucy Ambassador program, which is what Jonathan is participating in now. So with this, you will be trained to learn how to teach the public, and the public, that's all on the age range that you decide, from little kids all the way up to adults. And so this requires a 1-year commitment, and internships would be 10 weeks. With the Lucy Mission internships, so that they would be partnered up with, say for instance, NASA Goddard Flight Center. You also have, there's also, oh yes, so the NASA Goddard Space Flight Center, Southwest Research Institute, and Lockheed Martin, Arizona State University, and forgive me, I might mispronounce this, Connectix. But so the only difference is Arizona State University, that's a 5-week internship, the others would be 10 weeks. So this is the QR code. You can scan it if you want to get more information. It goes directly to the website. You can also email the faculty if you have additional questions. And so it's an amazing experience. I knew I wanted to be in a STEM career, but I just didn't know where to go. I didn't know what industry I wanted to go into. And so one of the best things about this academy or this program is you also gain lifelong friends. Maybe not in your team, but you can also within the class, and you would keep in touch, even up to this day. Some of my peers, end up being better friends than what I am in person. So, but they're amazing because they're all like-minded, all very supportive. And it's very, you know, sometimes, especially in a STEM major, we all know how difficult our classes are. And so we need the positive support system to help get us through and to help study together, because we can't, it's, you know, it's best to learn together because there's always something you can learn from someone else, and as well as they can learn from you. So, you know, just like in aerospace industry or any type of STEM industry, it's all team-based. It's all team-based learning environment. We all learn from each other. We help each other and support each other. So yeah, and I do want to give a quick shout out, including Zoom attendees. I want to give a quick shout out to a group of students, the students with disabilities. I myself, I have a disability. My eyes and my brain do not coordinate consistently, so it's called convergence insufficiency. So I have a difficult time reading comprehension. It takes me a longer time to read and understand what I'm reading. So it can take me a long time to do my homework and study and everything. And so the reason why I'm giving a quick shout out to students with disabilities is I know sometimes it can be really scary, especially if you're comparing yourself to, you know, another student, but you know, just go for it, reach out for support, reach out for help. You know, some of the brightest professionals today do have some form of disability, but they're doing amazing. They're, you know, don't give up, but just reach out for help. We're all here to succeed together. Thank you, everyone.
So Mariam in the chat says, great presentation, April, and congratulations.
Thank you. Thank you so much. So one thing I wanted to share real quick, I know Jonathan wanted me to also share. So with MP, we were in different teams, but we did participate it last year. So with my team, I was also a project manager for my team for the proposal writing, and my team ended up being the one of 3 teams selected by the NASA panel to receive the $10,000 grant. And so we are able to now advance our proposal into the redesigning, manufacturing, and testing phase. So currently what we're doing right now is we're currently redesigning our proposal. So in general, what we're trying to do is we're trying to improve the thermal performance of the rocket propellant tanks. So
That's cool.
yeah.
And one other comment from the chat, Diana says, yay, PS, congrats, April.
Thank you. Thank you.
And I did put this in the chat. If anyone has questions, type them, or people in the room, feel free to ask.
Oh, yes.
Is this all this information in the club, or where do we?
So so it's all on the website on ListSpace. It's, even though it's based out of Arizona State University, it's all virtual. So anyone in all students.
Minority serving institutions are preferred, so.
Yes.
And if you want, I can take this slide and email it to everyone who registered or everyone who attended. You could let me know what you
Yes.
prefer.
Yes. Yeah.
Yeah.
And then if you have any questions, you know, I can also give you my email as well. You can reach out to me personally.
And there's one thing that I thought was worth mentioning between the 2 academies. They're slightly different in their flavor and what type of activities you do. In the MCA, Mission Concept and Academy, you're basically designing a spacecraft mission from the ground up. You and your team, you're designing the whole thing, kind of like we saw with that Lucy the space mission. That process happened for that NASA mission, Lucy in Space. Somebody designed it from the ground up. And then in the NASA proposal writing, what you'll do is you're actually developing a new technology concept. So you as an individual, each person in the team, you have to think about different problems that you see that would be space related generally, but it could be almost anything. And it basically is, you know, come up with a concept. I think if you like, one of the concepts I came up with was like pumping cryogenic fluids under the lunar regolith to store energy and to store trapped heat energy and to dissipate heat energy, because in space, getting rid of heat is actually a hard thing. but on the moon, you don't. So it's a concept, right? And so in my team, that was the concept we actually ended up going with. But we had great ideas from every single other person. So what's fun is you come up with this idea, and then in the academy, in the NPB Academy, they teach you a lot about intellectual property and understanding like that. And you actually register your concepts, the team's concept, you actually register it with NASA as a new technology report. What happens is that actually goes into a database at NASA, so that then if that idea, that concept that you came up with, somebody else wants to do it, it's like a patent. So if somebody says to NASA, hey, we're interested in cryogenic storage or something like that, they'll actually do a search, and your concept will be one of those potentials that they could license with NASA. And then you and your team actually get brought in to work on that in the future if you want to keep advancing that concept. So kind of fun stuff. It gives you a lot of exposure. You get a lot of exposure with people at NASA in that academy as well. So anyway, some fun stuff.
Yeah, definitely. Thank you for adding that.
Yeah.
Yeah, and as far as the chance to win the prize, the seed funding prize, typically they aim for, one team per term. But, there is, just like with the term that we were in, it was really competitive to where the panel couldn't choose within the three. So they were able to find the funding to fund all three teams that they wanted to keep. So, yeah.
Let's go ahead and give one more round of applause. Sometimes Harris at the beginning, I did also want to thank Professor Horwath for being here and share engineering classes that we are offering in the winter and in the spring. They'll be on the course schedule, but here's a sneak peek of what we're going to be offering. And last but not least, please do, online attendees, in-person attendees, scan the QR code that's going to appear on the screen. That is our evaluation, so that you can give us feedback. Sorry, it's taking a minute to appear, but it should. If not, I can hold it on my laptop. But it should be appearing soon. I really want to thank everyone who attended. I want to thank the Glendale College Foundation, who sponsored the lunches. I want to thank our engineering faculty, all the faculty who shared this with you, all the student clubs who shared this with you. I want to thank our culinary arts department for providing the lunch that we had. And of course, last but not least, our career education department. There's Gabby, she's one of our other counselors. And okay, I said last but not least, but of course, you all for sharing about this program. I had never heard of it before April brought it to my attention, and I was like, more people need to know about this. So I hope some of you are considering applying.
Yeah.
Thank you. Stop sharing. Oh yeah, my Zoom keeps disconnecting. So
It's from the background.
that's the old
That's
one.
the wrong one.
Yeah.
That's ours.
Zoom attendees, I'll put in the chat once I get connected again. My laptop is mad at me for trying to do so many things. All right, but I'll use that. I'll stop the recording. Yeah. And then for those who are here in person, you can follow up with our presenters a little bit.